Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the video lecture series on linear time invariant system using Fourier transform and Laplace transform. Linear time invariant system are characterized with the help of differential equation, impulse response, block diagram representation, state variable description and transfer functions. First, what is meant by differential equation? It is used to represent continuous time linear time invariant system. It relates the input and output of the system. When we giving the input to your differential equation which produces the output as y of t. System transfer function, ratio of output to the input, h of s is equal to y of s divided by x of s. What is mean by frequency response? It can be replaced by omega. H of omega is equal to y of omega divided by x of omega. The input function x of t can be applied to your Fourier transform which produces the output as x of omega. That is nothing but your frequency domain analysis h of omega, which can produce the output as y of omega. For y of omega, we are applying the inverse Fourier transform which can produce the output as y of t. Condition for a linear time invariant system to be causal, h of t is equal to 0 for t less than 0. Condition for a linear time invariant system to be stable, summation k is equal to minus infinite to infinite, modulus of h of k should be less than infinite. What is mean by impulse response? Impulse response is the output generated by the system when a unit impulse is applied at the input. X of t is equal to del of t that can be applied to your linear time invariant system which can produce the output as impulse response as h of t. H of s is equal to y of s divided by x of s. Finally, how to find the impulse response of the system? H of t is equal to inverse Laplace transform of h of s. Next, Fourier transform. Fourier transform can be applied for both periodic and non-periodic signals. It can be represented in frequency domain. It provides an effective reversible transformation link between frequency domain and time domain representation of the signal. The spacing between the spectral components becomes infinitesimal and hence the frequency spectrum appear to be continuous. Periodic signals has a fixed time period as t0. This is the time domain representation into frequency domain. The complete time period can be represented as your t that can be represented as frequency domain in terms of 1 kHz. Similarly for 2 kHz. 2 kHz the signal can be represented in terms of that can be one signal can be divided into half, that is t by 2 which is 2 kHz that can be represented in terms of frequency domain. Next, first we can apply your analysis function and your synthesis function. When we applying the s of t to your analysis function which produces as s of f. Thus s of f can be applied to your synthesis function which can produce as the s of t. S of t and s of f forms the Fourier transform pair. Next one is Laplace transform. It represents the continuous time signal in terms of complex exponential e power minus st. Laplace transform can be used to analyze signals which are not absolutely integrable. Continuous time signals can be also be analyzed effectively by using Laplace transform. Laplace transform of impulse response is called as system function or transfer function. Laplace transform is divided into unilateral Laplace transform and bilateral Laplace transform. When we are applying the x of t into Laplace transform, while we are applying the Laplace transform of x of t which produces as x of s, in terms of h of t, h of s, output y of t is equal to h of t into x of t. By applying inverse Laplace transform which can produce as y of s is equal to h of s into x of s. First one can be represented in terms of time domain. Second one that can be represented in terms of frequency domain. This is your time domain representation. First for your linear differential equation we are applying the Laplace transform which can produce as the Laplace domain or complex frequency domain. That linear differential equation can be applied to your time domain which can produce as your time domain function as your h of t, right? While we are applying your Laplace transform function that can be applied to your Laplace solution, then we apply the inverse Laplace transform, we can get the time domain solution. How to find the impulse response? First differential equation, then we apply the Laplace transform for the algebraic equation and solving for the roots. Finally for that roots we are applying the inverse Laplace transform, we can get the impulse response of the system. What is mean by convolution integral? Any input can be expressed using the unit impulse function is nothing but your convolution integral. While we applying the input x of t to your linear time invariant system, which can produce the output as y of t. Y of t is equal to time domain into x of t. Y of t is equal to x of t into h of t. Convolution integral can be represented as x of t is equal to integral over minus infinite to plus infinite x of tau into del of t minus tau into d tau. Next, properties of convolution integral: commutative property, associative property and distributive property. Commutative is nothing but your x of t multiplied with your h of t, which is equal to h of t into x of t. Distributive, x of t into h1 of t plus h2 of t, which is equal to x of t into h1 of t plus x of t into h2 of t. The left hand sided sequence diagrammatic representation, right hand sided sequence x of t multiplied with your h1 of t, h2 of t, finally going to sum, which can produce the output as y of t. Distributive property: x of t multiplied with your h1 of t, again multiplied with your h2 of t, which can produce x of t into h1 of t into h2 of t. Left hand sided sequence, right hand sided sequence: x of t multiplied with your h1 of t, again multiplied with your h2 of t, which can produce the output as y of t. X of t multiplied with your h1 of t into h2 of t, which can produce the output as y of t. These are the basic signals involved in your linear time invariant system. U of t is nothing but your unit step signal. 1 for t greater than or equal to 0, 0 for t less than 0. Next is unit impulse function. Del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. Unit ramp signal is nothing but your linearly growing function. R of t is equal to t for t greater than or equal to 0, 0 for t less than 0. The diagrammatic representation also be represented. Next one, find the Fourier transform of x of t is equal to u of t. X of f is equal to integral over minus infinite to plus infinite x of t into e power minus j 2 pi f t into dt. U of t condition is 1 for t greater than or equal to 0. That's why we can applying the limits from 0 to infinite. We can get the answer as x of f is equal to 1 divided by j 2 pi f. Next one, Fourier transform of unit impulse function. Whatever the function will be taking for unit impulse function, else Fourier transform, Laplace transform or Z transform, the output will be as your 1. Next is your Laplace transform of x of t is equal to u of t. X of s is equal to integral over minus infinite to plus infinite x of t into e power minus st into dt. U of t means 1 for t greater than or equal to 0, 0 for t less than 0. While we taking the limits from 0 to infinite, we can get the x of s as 1 by s. Similarly, for x of t is equal to r of t, for applying as a t into e power st, we are applying here as a UVD method. We are getting the answer as x of s is equal to 1 divided by s square. Finally, Laplace transform of unit step function is 1 by s. Laplace transform of unit ramp signal is 1 by s square. This is the Laplace transform results we are getting from your LTI system. If the system produces the output y of t is equal to e power minus t into u of t, for an input x of t is equal to e power minus 2t into u of t. We determine the impulse response of the system. Y of t is equal to e power minus t into u of t. We can get y of f is equal to 1 divided by 1 plus j 2 pi f. X of t is equal to e power minus 2t into u of t. X of f is equal to 1 divided by 2 plus j 2 pi f. We can find out the frequency response. H of f is equal to y of f divided by x of f. 2 plus j 2 pi f divided by 1 plus j 2 pi f. While we applying the inverse Fourier transform of this h of f function, we can get the h of t is equal to del of t plus e power minus t into u of t. Next, these are the sum of the Laplace transform results. E power minus t into u of t is equal to 1 by s plus 1. Minus e power minus 2t into u of t, which is equal to minus of 1 divided by s plus 2. E power minus t into u of t minus of e power minus 2t into u of t, which is equal to first results 1 divided by s plus 1 minus of 1 divided by s plus 2. E power minus t into u of t minus of e power minus 2t into u of t, we can get 1 divided by s plus 1 into s plus 2. Now we can see the assessment. The system transfer function is given by h of s is equal to y of s divided by x of s. List the properties of convolution integral. It can be divided into three properties: commutative property, associative property, distributive property. Dash relates the input and output of the system differential equation. What is mean by impulse response? When the unit impulse is applied at the input, which can produce the output as h of t. That is nothing but impulse response. Define unit step and unit impulse. U of t is equal to 1 for t greater than or equal to 0, 0 for t less than 0. Unit impulse del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. The condition of an LTA system to be causal is nothing but h of t is equal to 0 for t less than 0. Fourier transform of unit step function is given by x of f is equal to 1 divided by j 2 pi f. The condition of stability of an LTI system is summation k is equal to minus infinite to plus infinite. Modulus of h of k should be less than infinite. Laplace transform of unit ramp signal is given by x of s is equal to 1 divided by s square. Linear time invariant system are characterized with the help of differential equation, block diagram representation, system transfer functions. Thank you.